Well, today we'll be talking mostly about parallel lines and lines that cross parallel lines, called transversals. The subject says identify pairs of lines. We're not going to run around spotting pairs. Oh, well, there's two lines, there's a pair. No, what we're talking about is identifying them as parallel or skew. Parallel lines, you're already familiar with, I'm sure. Pardon me. I'm sure you already know what parallel lines are. That doesn't look exactly parallel to me, but yeah, pretend those are parallel lines. In other words, they never cross, they never intersect, and they're in the same plane. You can have lines that take off at a different angle. I draw so badly, I don't know if I can do it, but we'll see. And then one that sort of takes off like that. But try to imagine depth. So we have this line here, and this one's actually under it. Let's say we're at now this one's 3 feet off the floor, and this one's 2 feet off the floor. They're not in the same plane, and although they look like they would intersect, there's a separation there in terms of depth that I'm not very good at drawing. That's why parallel lines have to be in the same plane. The fact that they don't intersect doesn't mean much if they're not on the same plane. Like these. They're kind of pointed as if they would intersect, but there's a depth separation between them. So they don't intersect. They're also not very interesting. These lines, which we can pretend are parallel, well, you can do a lot more with them. If they're in the same plane, then we know they're parallel. And they're much more interesting. For instance, we can cut them with another line. That's called the transversal. These, when they're set up like this, they're not in the same plane. That's called skew. This is the transversal, and these are, like I said, we're pretending these are two parallel lines. Think of them as parallel lines with perspective. You know, if you studied art, you know that you draw parallel lines in such a way that they appear to actually come together in the distance. So you would have, wow, that's really bad. And then there we go, like that. Except that I've exaggerated that way too much. It would be a little more reasonable. So when somebody draws railroad tracks, you see them getting closer and closer together as often at a distance. Because that's what it really looks like to you. That's just the way your eyeballs work. Doesn't mean they're actually coming together. It just looks like they are. But railroad tracks are not really the topic today. What happens when you cut two parallel lines with a transversal? Well, you make a whole bunch of angles, don't you? Look at all those angles. And we're going to look at some properties of these angles that we create when we cut parallel lines with a transversal. But first, a couple of postulates that we'll be using later on to prove things. That's what postulates are for. Now here's an important one. In fact, it might be the most well-known postulate on the planet. It's called the parallel postulate. When Euclid wrote his elements, he listed, I think, 11 initial axioms, and I believe the parallel postulate was number 5. Euclid didn't like it. He felt it violated Occam's razor. He thought there should have been a way to prove it. Consequently, he didn't use it for, was it almost somewhere between 200 and 400 pages into his book on geometry was the first time he used this parallel postulate, because he didn't like it himself. Turns out he had a point. It's not provable. However, it can be different. In other words, where it says there's exactly one line, you could leave all the other postulates in place and say that there were an infinite number of parallel lines. You could also leave every other axiom in place and say that there are no parallel lines. Each one leads to a different geometry. The first one I mentioned, the one with an infinite number of parallel lines, that's the geometry of a sphere. So Euclidean geometry, also called plane geometry that we're working with right now, is the geometry of a flat surface. And it makes sense. We live on what approximates a flat surface. Of course, you know the Earth is round, but look out your window. How round does it look? So, parallel postulate, if you study more math, it'll come up again. And if you don't study math, even in philosophy, it'll come up. It's a very interesting postulate that allows you to produce different kinds of geometries just by changing this one postulate and leaving everything else the same. The perpendicular postulate. Tell you the truth, I don't remember if there's a way to prove this one or not. But we're going to stick with, I think most books call it a postulate, so we'll stick with that. This one here, obviously, it says that there's exactly one line parallel, for instance. I think it's pretty obvious. You got a line here, right? You want to draw, there's another point not on the line, and you're going to draw a line parallel to it. How many lines parallel to it can you draw? Well, we're taking it on faith. We're just accepting the truth of the statement, there's only one. I mean, we're done. There's nothing to prove. That's the beauty of a postulate. It's true because we say it's true. Same thing down here. How many perpendicular lines are there through a given point, not on the line? Well, we're not going to prove that there's only one. We've accepted it as a postulate. But it kind of makes sense to me. I don't know. How's it look to you? If you can find another one, go for it. Well, there's our postulates. I don't think we have any more. Now, we need to identify some angles here. How about this angle? Let's call it A. What the heck? And let's call this one B. What can we say about these two angles? Well, first thing we can say is give them a name. Naturally, we got to have our own language here. In our math vocabulary, these are called corresponding angles. So you kind of see the sense of why they would be called corresponding angles. These two lines are almost identical. They're just moved a little bit. You could say that this line is a reproduction of this line, just moved that way a little bit. So when this line intersects this transversal here, you find it easy to believe that this angle would be exactly the same as this angle. That this line would intersect the transversal at exactly the same angle that this line does. I would find that pretty easy to believe. I hope you do. But we're not going to get too involved in the congruence of these angles yet. First, we have to give them names. And then we're going to find out which angles are congruent and which ones aren't. Corresponding angles, A and B. Now, what about over here? Well, how about B prime and B? No particular reason, we'll just try it that way. These are called alternate interior angles. Your teacher's probably got this with you already. These are the kind of things you just have to open your book and memorize. It's not like you're going to be bored knowing this stuff. Alternate exterior angles. Well, kind of makes sense that, what would your guess be? These are alternate interior angles. Alternate means opposite sides of the transversal. Interior means they're inside the parallel lines. Exterior, well, that would be a good guess for alternate exterior angle pair, and in fact that is called alternate exterior angles. Well, you see we have one pair type left, don't we? What about these two? I guess I'll call that C. C and B, what are they? Consecutive interior angles. Okay, that's our vocabulary. A and B, corresponding angles. B and B prime, alternate interior angles. A and A prime, alternate exterior angles. B and C, consecutive angles. And this section is, hold on a minute. This section is actually fairly easy. We're not going to prove too much about these group of angles we just created. As you can see, we take two parallel lines, cut it with a transversal, and we create 8 angles. Right now, we're more interested in making sure that we can identify these, the transversal, the parallels, and the angles. Mostly, this section is all about beating vocabulary into your head. Hope it doesn't hurt too much. We have an error analysis problem here. Describe and correct the error in saying that angle 1 and angle 8 are corresponding angles in the diagram. Well, it'd work a lot better if we had a diagram, wouldn't it? Let's take a look. Oh, there's a diagram. Angle 1 and angle 8 are corresponding angles. I don't think so. Remember? The corresponding angles were the ones that were, well, you kind of think of them as the same angle. If you think of this line as the same line as that, just shift it up a bit, then this is the angle where it intersects the transversal, and so is this. There. The word corresponding kind of fits. Just as when we refer to these as alternate, because they're on opposite sides, and interior, because they're inside the parallel lines. See, these, a lot of these definitions are actually kind of making sense, aren't they? They're ridiculously arbitrary. The more they fit the English words that you're used to, the easier they are to remember. Angle 1 and 8, corresponding angles. Well, there's angle 1 and there's angle 8. There's angle 8. They are not corresponding angles. 1 and 5 are corresponding angles. 2 and 6 are corresponding angles. 1 and 8, well, just like over here, those are alternate on opposite sides of the transversal. Exterior, outside the parallel lines. Alternate exterior angles, not corresponding. Pretty easy. And there's a few more simple problems. Like I said, this section is mostly about identifying the lines and angles we just talked about. This is so easy, you're going to feel like you're stealing your grade. If two lines are parallel, then they are sometimes, always, or never coplanar. The answer, of course, is always. That's part of the definition of parallel. They have to be coplanar to be considered parallel. The fact that they don't intersect isn't enough. They have to be in the same plane and not intersect. Then they're parallel. Otherwise, they're not in the same plane, they are askew. So the answer here is always. If three lines intersect at one point, then they are sometimes, always, or never coplanar. Well, three lines in the same plane certainly could intersect. And they could intersect all at one point. That's allowed. On the other hand, they don't have to be in the same plane, do they? Matter of fact, when you draw your coordinate plane in 3 dimensions, which you haven't done much of yet, but you probably will eventually, you'll have your something like that, and then your y-axis taken off like that. Now these are most definitely not coplanar. They intersect at one point. Even though I drew them in segments, they actually take off in all directions. They intersect here at one point. Now you've got, this is your xy plane here, this would be your xz plane here, and this would be your yz plane here if this were x, y, and z. So these definitely would not have to be coplanar. In fact, that's a very common example of 3 lines which intersect at one point. And actually, these 2 lines are in one plane, these 2 are in one plane, and these 2 are in another plane. So you actually got 3 planes coming together here. So the answer is sometimes, because these lines could, obviously they could be. I mean, you can go, there's one, there's another, all on the same plane. You could have an infinite number of lines which are all coplanar and all intersect at one point. It would be kind of messy, but you can do it. What about this one here? RPQ. Well, which one is RPQ? Well, there's RPQ. Okay. PRS. And this is PRS. So let's label these in a way that's easier. Like, let's call this one A. And this one B. Well, RPQ, well, there's A right there. Well, PRS, well, there's B over there. Now, this is a parallelogram. They don't say so explicitly, but I think you're supposed to assume that's what it is. That means these 2 sides are parallel, and these 2 sides are parallel. Well, this is the angle made with the transversal cutting these 2 parallel lines. And this is just like, well, this and this, or if I had completed the whole thing, it would be this and this, because this is really more sort of on the left side, I guess. So if we orient it like this drawing, then I guess this would be like C and C prime. And what are those? Alternate interior angles. See? Easy. Just have to learn the definitions in this section. Here's a couple more easy ones. Angle BCG and what are corresponding angles? Well, remember, what are corresponding angles? Those are the ones here and here. So, with angle BCG, where is that? BCG. Okay, so that's the angle right here we're talking about. And what is the other corresponding angle? I would say it's this one right here, wouldn't you? GJH. The instructive thing about this particular problem is that it points out all these angles we create when we've got 2 parallel lines cut by a transversal. These lines don't have to be parallel for there to be cut and still have the same definitions. When the lines are parallel, these angles have some special properties that we'll get into in the next section. When they're not parallel, they still have the same names, but not necessarily the same properties. So, the fact that this line and this line that is being cut, we'll just call this one the transversal, and these the 2 lines being cut by the transversal, they're not parallel. We can still identify the angles. These are corresponding, like this one and this one would be alternate interior, that and that would be alternate exterior, just as if the same definitions apply to when they're parallel or when they're not parallel. What doesn't apply is the theorems that we're going to prove in the next section regarding these various angles. But the names are the same. What about BCG and blank are consecutive interior angles? Well, BCG's there. Consecutive interior, remember, not alternate, consecutive. So, boom, there we are. And it's this one right here. We could call that alpha double prime. Well, I can't even do 2 primes with this. Or call it anything you want. This is the consecutive interior angle. See, it's just a matter of ordering those definitions that are in your book and hopefully in your notebook by now. Well, this is one of those non-math sections where you just do lots and lots of memorization, which seems more like a spelling test than math, but you have to learn vocabulary in math too. And more vocabulary. What would you say? This platform, think of it as a plane, not a line. It lies in a plane, and then think of the ground as another plane. We all know it's really a sphere, but for practical purposes, we can consider it flat. Otherwise, it wouldn't make any sense. I mean, the question wouldn't make any sense. The world would still make sense, but this particular question wouldn't. I would say the platform is parallel. If it was perpendicular, anybody working up here would be hanging on for his life, wouldn't he? And skew, well, these are planes, and a skew plane doesn't even make sense. There's no such thing as skew planes. There's skew lines. Planes are either parallel or they intersect. It's because they take off to infinity in 2 directions. When that happens, if it's tilted in any direction, it's going to intersect the other plane. There's no way around it. For lines, that's not really true. You can tilt the line in such a way that it's not parallel to another line, but it also doesn't intersect the line because it's just in a whole different plane. The most interesting thing about this problem, I think, is that you have to figure out a mechanical way to hinge this platform so that whatever you do with this arm, you raise it, you lower it, you pivot this thing around, it doesn't matter. This thing, well, pivoting shouldn't matter anyway, but when you raise and lower this arm, this comes up and down, this thing here always stays level. If that didn't happen, the guy on the platform could be in tough shape. I mean, what would be the point of having a platform? You might as well just toss a rope over the pole right here and climb up. It would be safer than a platform that tilts, say, at 45 or even 90 degrees on the way up and tries to dump you out. What kind of a basket would that be? That would be a basket I wouldn't want to ride in. Well, not unless you put an air mattress down here and go for a ride. I guess that would be cool. But this not only is horizontal, which makes it parallel to the ground, but you have to keep it that way as this thing goes up and down. That, to me, is the interesting part. There's some mechanics involved in keeping this thing always level. Ask your science teacher about that. This one's kind of interesting, just because if they called them by the usual name, the answer would be pretty obvious. Here they call them horizontal bars. I don't know, when I was hanging out in the gym, we called them parallel bars, which would have made the answer pretty obvious, wouldn't it? Are those parallel bars perpendicular, skew, intersecting, or parallel? Well, I'd say that those parallel bars are parallel, wouldn't you? Horizontal bars, I guess that's a common term too. We always called them parallel bars when we referred to them at all. These problems are awfully easy. All you had to do was memorize the vocabulary. Well, that's about all there was to this section. Like I said at the beginning, it's pretty easy. I'm sure you didn't have any trouble. And it was one of the least mathematical sections in the book, or in this collection of videos. Normally, in mathematics, you don't get to just apply definitions. This was kind of like a geography class. All you had to know was where the rivers were and what the names of the cities were. Same thing here, you just had to be able to list the names of these various angles and types of lines. But all these names that we learned are going to come in handy in the rest of the chapter. We're going to use them over and over again. So I guess this is a good way to just get all the names stuck into your brain so you won't have to stop and think about it from here on. Now you're experts. And I'll see you in the next video.